please.
Thank you, Erik. Hi, everyone. My name is Yi-Chun Lu, and I'm thankful for this opportunity to share our work. Today, I will be mainly talking in the area of aqueous batteries. I thought it would be good to introduce the overview of my research activities. As Erik mentioned, we have activities in metal air, metal sulfur batteries, looking at the fundamental understanding of electrolyte interfaces, and then aqueous batteries and redox-flow battery. And today I will be focusing mainly on the aqueous battery and the redox-flow batteries. We actually built several in situ in-house characterization systems to understand battery chemistry. While we are operating the batteries, we would like to know what kind of side reactions, what kind of degradation mechanisms ongoing. So that's really very much dear to our heart. In addition to fundamental science, we also dedicate a lot into tech transfer. And so we founded Glucose Energy, looking into how do we commercialize large-scale energy storage for renewable energy integration and so on. So to begin, I'd like to start with the motivation for first part of my talk, aqueous battery. So we all know that non-aqueous battery, they have high energy density. However, they are flammable, and so in a lot of application, it may be a risk involved. For instance, EV, or of course, most importantly, large-scale energy storage. The larger the scale, the larger the risk could be. So if we looking at chemistries that beyond non-aqueous, we looking at aqueous battery. However, aqueous battery suffer from narrow voltage window limited by water stability. So from this plot, you can see that the voltage window that operated for aqueous battery is limited by the oxygen evolution and the hydrogen evolution. So we have to exclude a lot of material that's beyond this stability window. Recently, there are a lot of efforts in the area of a highly concentrated electrolyte trying to use a highly concentrated salt to stabilize water. So for instance, water in salt, a hydromelt, a lot of gray approach has shown much improved stability in the aqueous battery and expanded voltage window. However, these approaches involve highly concentrated salt, and they are usually involving high cost and potential toxicity issue. So therefore, when we started, we try to find a approach that can stabilize water without involving highly concentrated salts. So there is a phenomenon in the living cell called molecular crowding. It's actually talking about the property of the solvent or the liquid, like liquid could be modified when there is a large amount of large molecules such as protein around these solvents. And so when they reach high concentration, they can actually modify the activity of the water molecule. Therefore, we ask, can we utilize this phenomenon and to apply into the aqueous electrolyte and see we can reduce water activity by so-called crowding agent. And these crowding agents should have strong interactions with water. And so we come up with a series of water miscible polymers. They are low cost and eco-friendly. So our idea is to increase the water agent interaction so that we can discourage the water-water interaction. And so the weakened hydrogen bond network from the water-water interaction will help to strengthen the OH covalent bond, because now the water are surrounded by the crowding agent instead of the water. And so therefore the hydrogen bond strength between the crowding agent and the water is weaker than the water-water hydrogen network. So by doing such replacement, we hope to strengthen the OH covalent bond strength therefore discourage water splitting. So to start to test this idea, we started the very common crowding agent in biology, polyethylene glycol. And this polymer actually you can mix with water in any ratio. So we use, in this case, various of water concentration and various of pH concentration to try to understand how the electrolyte property will affect, will be changed as we change the pH content. And of course, as I mentioned earlier, these type of material are non-toxic and very low cost compared to the lithium salts. So first we look at how the voltage window change as we increase the pH concentration. So as we increase from 0%, so that would be the low concentration 2 mole lithium TFSI with no PEG, all the way to 70 and even 9 to the 94%. You can see the hydrogen evolution potential has been delayed significantly as we increase the PEG content. And so this supports the idea that the water splitting are suppressed by the presence of PEG. And so we further look into some of the reasons why this will happen. So as we increase the pH content from proton NMR, we see that as we increase pH content, the nucleus is more shielded and indicating a weaker hydrogen bond network, which is, as we mentioned earlier, as we replace water molecule with crowding agent, the strong hydrogen bond network between water has been broken. And at the same time, we also observe a improved, stronger OH covalent bond, blue shifted. So these two evidence are supporting our hypothesis. And therefore, we use this electrolyte with 94% PEG, 6% water to serving as an electrolyte and to test the LMO, lithium manganese oxide, and LTO as an anode, as a full cell. So first thing we thought it's important to check is whether in this, even though we're looking at voltage window are suitable for this material, we still need to check whether in the real battery there is side reaction happening. So we use the online electrochemical mass spectrometry to detect what type of gases are coming out from the battery operation. So you can see from first and 10th cycle, you can see both charging and discharge. There is no obvious hydrogen evolution or oxygen evolution happening in this type of cell using the molecular crowding electrolyte. And so this type of cell then can be operate more than 300 cycles at more than 80% capacity retention. So we thought it would be interesting to compare this low concentration, low lithium concentration electrolyte with other highly concentrated electrolyte. And we thought we found that it actually provide one of the widest potential window for water aqueous electrolyte. Another thing that was very interesting during our investigation is that some of the electrolyte, even though the voltage window seems to be suitable for LTO, LMO, sometimes you actually, if you use the mass spectrometry to detect the water splitting, you can see a lot of hydrogen evolution. For instance, the 21 mole lithium TFSI has a lot of hydrogen evolution in operation. Also, other type of highly concentrated electrolyte also see some trace of hydrogen evolution, but the molecular crowding electrolyte does not evolve hydrogen in this battery operation. And of course, the motivation of using aqueous electrolyte is for safety. So since now we reduce a large quantity of water, so we want to also check the safety. And so in this case, we can see that in addition to adding water into the PEG does help the reducing the flammability of this electrolyte. So this is a sort of a first attempt for this type of molecular crowding electrolyte using for aqueous battery. But of course, one of the drawback in our first attempt was that the PG electrolyte with water actually has very high viscosity, and that give rise a consequence in the low ionic conductivity. So in this case, we were only able to obtain a 0.8 millisiemens per centimeter. But compared to, say, water in salt, is significantly lower, right? So, but of course, other type of highly concentrated electrolyte also in a range of less than 1 millisiemens per centimeter. So we do want to improve this ionic conductivity. And the thought it's simple that, if we can use other type of water miscible polymer, but with lower viscosity, then we can significantly reduce the overall viscosity and improve the ionic conductivity. So PG actually have a very strong intermolecular hydrogen bond interaction between the molecules. So if we can remove such interaction and replace with PEG-DME, so in this case, the end group does not have the hydrogen bond interaction. And so this can significantly reduce the viscosity. And so you can see from this measurement that the PEG-DME has a much lower viscosity compared to the PEG. And of course, using this type of crowding agent, PEG-DME, you can make even the same percentage of a polymer, you can have a much improved ionic conductivity. And correspondingly, you will have improved polarization, a much reduced polarization compared to the PEG. In this case, at 1C, you have much reduced voltage heteristic. And of course, if you check the mass spectrometry, you also see no hydrogen evolution or oxygen evolution for the PEG-DME molecular crowding electrolyte. So this is really a beginning of this type of concept applying into aqueous electrolyte. And we do see a lot of papers coming out really applying molecular crowding electrolyte in various battery and different like zinc batteries or even supercapacitors. So really to looking into the mechanisms and also applying in different devices. The next part, I'm going to switch gear to flow batteries. And the motivation to investigate flow battery is really to looking into large-scale, long-duration energy storage. So for long duration, we want to be able to freely extend the discharge duration. And flow battery actually offer exactly that kind of purpose. So for flow battery, we store energy content in the external tank, dissolving in the aqueous solution, and positive electrolyte, negative electrolyte, essentially dissolving the active material at the positive potential and negative potential. Then we can circulate the liquid electrolyte into the stack and separate by ionic conductive membrane. And then we can convert the chemical energy into the electricity through this device. So there are several features and also advantage of this type of flow configuration. For instance, in this case, power and energy are decoupled, meaning that you can freely scale the energy without having to change the power stack. So if you want going from 2-hour to 10-hour duration, you can just scale up the tank without changing the design of the stack. So that's very easy to scale up. Of course, if you use aqueous electrolyte, then it will be non-flammable. And also, it will be very easy to control the self-discharge, because if the device is going to be idle for a long time, then the pump can be just disabled, then you will have no self-discharge issue over a long period of time, right? So there's a lot of configurational advantage for flow battery. And like I mentioned, if you want to double the duration in the case of lithium-ion battery, you will just double the cost to buy 2 sets. But for long duration using flow battery, you can have added small cost using the electrolyte tank. And so right now the challenge for flow battery are several-fold. Essentially, we are looking at expensive electrolyte needs to be replaced. So vanadium is the most commercially available and also most mature flow battery chemistry. Vanadium 5, 4, and vanadium 2, 3 on the positive and the negative side. This battery system is quite mature, but it's limited by the high cost as well as the limited energy density. Right now, it's about 25 to 30 watt hour per liter, which is much lower than most of the other rechargeable battery system. So we decided to look into something more earth abundant and something intrinsically low cost, intrinsically safe. So we're looking into sulfur. Polysulfide in aqueous could be a potentially much easier to scale up since it's very cheap. So the cost for storage compared to vanadium, it's 1,000 times cheaper. And so globally, it's also the annual yield is actually also significantly higher than vanadium. And so with this intrinsic advantage, back in 2016, we put together a polysulfide iodide flow battery, just try to find a couple that we can demonstrate this type of system. And at the time, we were able to look into some of the different concentrations. So both iodide and polysulfide has very high solubility. So potentially it can actually provide theoretically 80 watt hour per liter. And at the time, we actually achieved around 50 watt hour per liter. But one of the most critical challenge for polysulfide flow battery is the lifetime. So you can see back in 2016, we using the commercial Nafion membrane, we were able to only cycle for 50 cycles. And this is really due to the crossover of polysulfide as well as the water migration. And so we decided to look into this issue by modifying the Nafion membrane. And so there are several issues we need to address, right? So we want to reduce polysulfide crossover and also polyiodide crossover. We also want to reduce water migration. And the water usually, the polysulfide actually sometimes come with water together migrating through the membrane. So to stop this crossover, we decided to have a coating that consists of a hydrophobic polymer binded carbon. And the role of the hydrophobic polymer, PVDF in this case, is to reduce the water migration and really to reduce the water affinity. And the carbon on each side is actually try to absorb polysulfide and polyiodide, and so that when they are immersed into these anions, they will be charged, and to further prevent further crossing over through this layer. So we call them charge reinforced, because in our design that we hoped that they can reduce the same charged ion from further crossing over. And so that's the idea of this type of coating apply on the Nafion membrane. So while this is a very, I would say, simple idea, it actually is surprisingly effective. So you can see the polysulfide flow battery using Nafion membrane, from 1 to maybe 50 cycle, you almost decay more than half, and after 300 cycle, all the capacity are mostly gone. And this is exactly the issue that all the previous polysulfide flow battery are facing. So with this increased membrane, this membrane modification, you can immediately see a huge change in the charge-discharge profile. And again, this is really operating at 100% SOC, looking at very deep, deep DOD. And with this type of test, we can cycle this polysulfide flow cell for more than 3 months without degradation. And using commercial membrane, either one piece or 2 pieces, you can see the decay significantly over time. And so in the flow battery test, we operate for 500 cycles, more than 2,000 hours. And then after that, we did a check and realized that they still have more than 99% capacity left after 3 months. So this is really the first time that we can see stably utilizing polysulfide in the flow battery. So why this is so effective? So we try to understand more. So we use the small angle X-ray to understand the water cluster size. So as you can see, using crisp membrane, we actually are shrinking the water channels from 3.7 nanometer to 2.7 nanometer. So this is a significant difference, which can explain the reduced water uptake for crisp membrane and the reduced swelling as well. And we also use the in situ FTIR, try to understand how fast or how slow this water molecule can go in and out through this membrane. So we lock down the water peaks and observe the evolution over time as we hydrate and dehydrate the membrane. So you can see with Nafion membrane, you can see the water migration, water movements very, very much faster compared to the crisp membrane, which much restrained water activity, water mobility. And so the next challenge we need to address for polysulfide is the sluggish kinetics, right? So in most cases, you need catalyst, but then even using the reported catalyst, the round trip efficiency is roughly almost less than 50 or 60%. And so these are also from literature. This is very universal for polysulfide type of flow battery. And the reason is this polysulfide reduction from S42- to S22-, breaking sulfur-sulfur bond actually is very energetic, intense process. And so most of the reported methods is not very effective because, for one, the catalyst may not be very active. Second, the catalyst need to be very well dispersed, and they still have very limited active site. So we decided to go a slightly different route from, solid catalyst into looking to a soluble catalyst, so a molecular catalyst. So essentially, instead of directly electrochemically reduce polysulfide, we reduce a redox molecule itself. So in this case, riboflavin sodium phosphate, FMNA. This molecule can be reduced with much lower overpotential, so much faster kinetics. And once it's reduced, it can react chemically with S42-, and to reduce S42- to S2- chemically, and itself can be reoxidized back to the oxidized phase. And so through this cycle, then the oxidized FMNA can go back, continue to receive electrons from the electrodes, and then to reduce chemically S42-. So this is a very simple scheme to essentially convert the sluggish electrochemical reaction to a very fast chemical reaction with a fast redox molecular catalyst. And the first thing you need to check whether this approach work or not is whether or not this reaction actually exists, right? So we assume that once we reduce FMN, we can chemically reduce S42-. So we actually can use a very simple ex situ UV-Vis. So you can see this gray line is the solution for S42-, and the blue line is the reduced form of the FMN. So once you chemically mix them, you can see immediately we will form as FMNA3+, 3-. So to indicate the charge transfer between the 5- of and the form S42- to form FMN3-. Okay, so this is a indication that this reaction actually exist. And then we go ahead to start putting, I think in this case, 5 to 10 millimole of the FMN into the polysulfide electrolyte. And so you can see without FMN, just the pure polysulfide is this light blue. At the 40 milliamp per square centimeter, you can see a huge polarization. And with FMNA molecular catalyst, you can have much reduced overpotential and much higher capacity utilization, right? Because now we can, the cutoff voltage will be far away from the actual plateau. And also what's encouraging is that this catalyst effect is persistent throughout the cycles, right? So that's also very important, that it has to be stable over cycles. So you can see that not only it will improve the rate capability, but also it improve the cyclability, because now we can access most of the capacity in the electrolyte without reaching the cutoff voltage, right? Because the kinetics is significantly improved. And so we also looking to more evidence that we actually are directly improving the overpotential of the polysulfide side. So then we operate this 4-electrode system, so you can decouple all of the potential using the reference electrode. So the red profile show so this gray line on charge and discharge, that's the overall cell voltage. And you can separate them into the positive electrolyte, polysulfides, and the membrane overpotential, and then negalite potential. So the cell with FMNA and the without FMNA, you can see they have a huge difference on the overpotential at the negative electrolyte side. And so this is further indicate and support that this molecular catalyst indeed reduce the overpotential at the polysulfide side. And so we're looking into the rate capability of this cell, because very often as we increase the rate capability, the power and the current density, you will reduce the capacity. In this case, we do see increase of overpotential, most likely because of the membrane, but you can see we still can access the 100% of the capacity, even at 80 milliamp per square centimeter. So we are curious whether this overpotential, whether it's mostly from the membrane. So we did a simple IR correction just to look at what if we remove the dominant membrane ohmic drop, what would be the profile look like? You can see they are overlapping perfectly, even from 10 to 80 milliamp per square centimeter. So this shows the potential of this catalyst for polysulfide flow battery. And so we also looking to operantal UV-Vis spectroscopy, try to understand the interaction between the catalyst and the polysulfide. So so essentially you're looking at the charge discharge profile as we operate the UV-Vis. And what you're looking at, the first on the left side, the A panel, looking at only FMN. So as we reduce FMN, you can see the FMN3 minus forming to FM5 minus, and then forming back to FMN3 minus. So this is the changes that you will see with FMN alone, okay? And with polysulfide, in the range that we are looking at, there is not much change during this charge and discharge. And so once you put them together, once you put the FMN into the polysulfide electrolyte, there's something interesting you can see. So first of all, we are still, as we charge the cell, so initially you will see FMNA to reduce from 3 minus to 5 minus, and you will see the color are reducing. But in the case if you have S4 2 minus, you will see that the FMNA 3 minus will not decay as fast as the one just with the catalyst. Essentially, it's indicating that the FMNA3 minus has been regenerated in the presence of S4 2 minus, right? So otherwise it will be dropping and forming 5 minus. But in this case, we are continuously regenerating the 3 minus through this chemical reaction with polysulfide. And so this, you can see that is another indication of the mediation process that we designed through the molecular catalyst. So looking at the stability of this type of cell, so you can see the cell without FMN, you can have stable with the crisp membrane, but the capacity is quite low. But if once you add FMN, you can have much reduced overpotential and much improved energy efficiency. We also do another test where for the cell without FMN, as we show in the light blue here, after around 900 cycle, we add FMN to the exact cell, and then you can see the capacity just jump significantly from around 60 to 120. You can see this is a direct proof of the effect of the molecular catalyst. So in the long-term cycling, we cycle for more than 2,000 cycle and more than 1,200 hours, and to extrapolate the decay rate. So this is again not only very low decay rate, but also we can operate at much higher current density than before. We also further scale up this system and looking at amp level of the type of cell. So it's 100 milliamp per square centimeter tested in a 100 centimeter square cell. So you can see still operate quite stable at scale up electrolytes. The last work I want to share in the flow battery is really targeting for low temperature application. So extreme cold weather reduced the range of flow battery application, and so of course also for EV, but for a grid scale storage, we need to really withstand the cold. So we decided looking to what type of material would be more suitable for extreme low temperature application. And we decided there are several things that are important. First, at the low temperature, the kinetics will be significantly reduced. So the material initially should have very high kinetics. Second, we need to have low freezing points, right? So the electrolyte, usually, I mean, water medium electrolyte freezing point needs to be much lower than water. And we need to have high conductivity because, again, at the low temperature, you will have reduced conductivity. And also, we also want to have high concentration of the active material to preserve the energy density. So we look into literature, and this polyoxymetallate type of material caught our attention because, again, it has a very high kinetics itself, and also it has 60 electrons active that can be stored in this POM. There are some literature showing up to 12 electrons storage, but in our case, we see that a lot more electron at the end are mostly hydrogen evolution. So we decided only stick to 6 electrons, and which is already pretty good, and that's also very important to avoid side reaction of hydrogen evolution. So then in the literature, the lithium cation is also what's used in the flow battery, but we decided to go for proton. So this proton type of HPOM, we believe that will be more important for the low temperature application. And here are the reasons. So we look into the cyclic voltammogram to understand the kinetics as we change the temperature. So you can see the HPOM at the 25 degrees Celsius and the negative 20 degrees Celsius. You see that the cyclic voltammogram does not change significantly over a very wide temperature range. But in contrast, the vanadium 2+, 3+, which is the nickelite of the old vanadium flow battery, has a significant impact on the kinetics as we decrease the temperature. So this indicates that HPOM will survive much better at the low temperature environment. And then we also look into the differences between different cations in the concentration of POM, right? Because we need to maximize the POM concentration. So the proton form will have a much higher concentration compared to other cations, lithium, sodium, potassium. And this is because the hydration shell of the proton, total hydration cation, actually will have much weaker binding with POM because the hydration shell is smaller. So you can see in this case, the weaker binding will provide higher concentration, higher solubility of the POM. So these also are supported in the concentration measurements. And then the next, of course, is the freezing point. The HPOM, we detect down to negative 35 degrees Celsius at the 0.5 mole is still maintained as liquid form. But other type of cation already frozen at much higher temperature. And so this again further indicate the proton POM is a very critical factor if we want to maintain the low freezing point. Then it's the conductivity. Benefited from the special Grosser's mechanism, ion conduction hopping mechanism. This HPOM has much higher ionic conductivity at low temperature compared to other ionic conduction mechanism operated by lithium, sodium, and potassium. At the negative 20 degrees Celsius, it can even reach more than 70 millisiemens per centimeter. So looking at the full cell, we couple this HPOM with vanadium 4,5 and to couple to see the full cell operation. At the room temperature, this HPOM can operate at extremely high power density and high current density. So we can run from 100 milliamp per square centimeter to all the way 500 milliamp per square centimeter. And the stability is also very reasonable. Of course, the most important thing for us at the time was to understand the low temperature performance. So we bring the temperature down to negative 20th degrees Celsius and looking at the rate capability from 100 to 240 milliamp per square centimeter. And the cell can still provide more than around 300 milliwatt per square centimeter. And the stability can sustain for more than 1,200 hours and more than 1,000 cycles at negative 20 degrees at 160 milliamp per square centimeter. Right, it's a very high current density for a low temperature operation. And even after cycling, we can observe no structural changes of this type of material. And so to put them into context, right? So low temperature operation for flow battery is very challenging, can be evidenced from, say, if you use vanadium, all vanadium, V2, V3, V4, V5, even at 5 degrees Celsius, 40 milliamp, you can already see huge decay, not to mention at negative 20 degrees Celsius, 160 milliamp. But for HPOM, you can operate a very high current density at the low negative 20 degrees Celsius. So this is the comparison also with other type of zinc iodide, for instance, also cannot sustain at the low temperature. So this is, I believe, is my last slide, since my time is also up. We also wrote a perspective to share about the assessment method and performance metrics for flow batteries, and looking into what type of cell configuration for long-term stability test, what type of analysis will be important for different type of flow battery, right? So today I only discussed the all liquid type, but a lot of time you will involve zinc metal as one side, and so you may look into dendrite formation and so on. And so I believe that this is I guess a little bit on the educational side, will provide some of the insights into how to test and how to find out why the battery is decaying and what should we pay attention to. So with that, I'd like to thank the funding agents and also students and postdocs for their work, and I'm happy to take questions.
Thank you very much, Yi-Chun, for a very nice talk.